A modern electric vehicle may depend on something most people have never seen. Not the battery, not the motor, not even the chip that usually gets all the attention. It may depend on a small white ceramic sheet, roughly the size of a palm, covered with copper and carrying black semiconductor devices on top. It does not look dramatic. It does not look expensive. It sits quietly inside the power electronic system of an electric vehicle. But without it, the inverter cannot work reliably. The power module cannot survive extreme heat, and the electric drive system cannot deliver stable performance. This component is called a ceramic copper-clad substrate. In high-performance EV power modules, the most important version is the silicon nitride AMB ceramic substrate. It is the foundation of a power semiconductor module. A normal circuit board is usually made with resin-based materials. But an EV inverter is not a normal circuit environment. It has to convert direct current from the battery into alternating current for the motor. During that process, power devices face high voltage, high current, high switching frequency, and extreme thermal stress. As 800-volt platforms and silicon carbide power modules become more common, the demands become even higher. The material under the chip must conduct heat, provide electrical insulation, resist cracking, and survive repeated heating and cooling cycles. That is why ceramic is used. But this is not ordinary ceramic. It is not the kind of material used in household bowls or tiles. It is silicon nitride, with the chemical formula Si3N4. Silicon nitride is difficult because it must do several things at once. It must conduct heat efficiently, but remain electrically insulating. It must be mechanically strong, but not too brittle. It must tolerate high temperatures, but also survive the thermal cycling of real vehicle operation. Thermal conductivity, bending strength, fracture toughness, surface flatness, and thickness consistency all matter. If any of these fall short, the entire power module can lose reliability. For many years, China's electric vehicle industry expanded rapidly, but high-end silicon nitride AMB substrates remained heavily dependent on imports. Global market was dominated by a small group of overseas suppliers. Japanese companies built deep advantages in ceramic powder, substrate preparation, and precision manufacturing. Kyocera, Denka, and Dowa have long held important positions in this field. Germany's Heraeus has become a major player in power semiconductor packaging materials, with its Condura product family focused on silicon nitride AMB substrates. Rogers, through its Coramic line, is another well-known name in ceramic substrate technology. For a long time, the division of labor was clear. Japanese companies were strong in powder and ceramic sheets. German companies had advantages in brazing and metallization. American companies were strong in system integration and customer qualification. Chinese power semiconductor companies that needed high-end substrates often had to wait in line. That is the real supply chain bottleneck. It is not always about a total ban. Sometimes the bottleneck is delivery time. Sometimes it is pricing power. Sometimes it is the fact that the supplier controls the schedule while the customer must adjust its production plan around imported materials. During the fastest expansion phase of new energy vehicles, long delivery cycles for high-end ceramic substrates became a serious problem for domestic module makers. The issue was not only cost. It was whether a production line could start on time. High-end imported silicon nitride AMB substrates are not cheap. Depending on specifications, the price can reach hundreds of yuan per piece. Traditional DBC substrates using aluminum oxide ceramic cost much less, but they cannot meet the same performance requirements in high-end silicon carbide modules. For 800-volt platforms, high power density, and long vehicle-grade reliability, AMB substrates are becoming difficult to avoid. The challenge lies in the process. It begins with powder. The purity, particle size distribution, oxygen content, and impurity control of silicon nitride powder directly determine the quality of the final ceramic sheet. If the powder is not right, later processing cannot fully fix the problem. Then comes forming. A mainstream method is tape casting. In simple terms, ceramic slurry is spread into a thin sheet with extremely precise thickness control. There can be no bubbles, no uneven settling, no hidden microcracks. A tiny defect at this stage can become a major failure after high-temperature sintering, then comes sintering. Silicon nitride requires high-temperature sintering under controlled conditions, often above 1,800 degrees Celsius. The heating curve, holding time, pressure control, and gas atmosphere all influence the final microstructure. Leading overseas companies have accumulated decades of know-how in these process windows. After sintering, ceramic sheet must be cut, ground, polished, and then metallized. This is where AMB technology becomes critical. AMB stands for active metal brazing. Its purpose is to bond copper foil firmly to the ceramic surface. Traditional DBC, or direct bonded copper, works for aluminum oxide ceramic, but it is not ideal for silicon nitride. Silicon nitride does not bond directly with copper in the same simple way. AMB uses an active brazing material, often containing titanium as an intermediate layer. Titanium reacts with the surface of silicon nitride, forming a stable bonding layer. The copper foil is then bonded through the brazing material. The process must be carried out under vacuum or protective atmosphere. Temperature, brazing composition, spreading, uniformity, heating rate, and cooling rate all affect final strength. After metallization, the substrate still needs photolithography, etching, printing, and surface treatment before the final circuit pattern is formed. Powder, casting, sintering, cutting, copper bonding, lithography, etching, and surface treatment. Every step is a technical barrier. If one step fails, the product cannot enter the vehicle-grade supply chain. That is why this small ceramic sheet is not just a material. It is a combination of powder chemistry, ceramic engineering, metal brazing, semiconductor packaging, and automotive reliability testing. The turning point came with the surge in electric vehicle demand. China is now the world's largest new energy vehicle market. As 800-volt platforms, silicon carbide modules, fast charging, and high-performance electric drive systems accelerate, demand for silicon nitride AMB substrates is rising rapidly. Imports may support a small number of premium models. But when demand moves toward tens of millions of pieces, relying entirely on overseas suppliers becomes unrealistic. At that point, localization is no longer optional. It becomes necessary. Chinese companies have been moving quickly into this field. Ferrotech-affiliated Fulehua, Bowman Electronics, Sonoma Advanced Nitride Ceramics, Fujian Huaqing, Zhejiang Zhengtian, Shanghai Kaiqi, and Nantong Wispower are among the companies involved across different parts of the chain. Some focus on copper-clad substrates and packaging materials. Some focus on powder and ceramic sheets. Some began in printed circuit boards or electronic materials and are extending into power semiconductor materials. Fulehua is one of the representative players in domestic AMB substrate mass production. Its production base in Neijiang, Sichuan, is designed around large-scale automated output and reflects the massive demand coming from China's EV supply chain. Neijiang sits within the Chengdu-Chongqing economic region, close to major auto and power electronics clusters. This location gives domestic suppliers a response speed advantage over long-distance imports. That local supply chain cluster is one of China's biggest advantages. In the old model, imported substrates could take months to arrive. In the new model, customer feedback, sample trials, thermal testing, and process adjustments can happen much faster. A power module company can send design requirements to a substrate supplier, receive samples quickly, run reliability tests, and feed results back into the next production iteration. This kind of fast interaction accelerates material localization. Another key change is engineering talent. In the past, high-end material processing relied heavily on long experience and repeated trial and error. Today, Chinese manufacturers are using simulation software, thermal field modeling, fluid calculation, automated inspection, and data-driven process control to optimize parameters. Engineers trained in material science, chemical engineering, mechanical systems, and electronic packaging are moving into factories, shortening the trial and error cycle and improving yields. At the early stage, some domestic AMB lines had relatively low yields, creating high cost pressure. But as production lines stabilize, process windows improve, and upstream and downstream players coordinate more closely, yield rates are moving closer to international levels. Some domestic products are already entering vehicle-grade validation or supply chain introduction. This does not mean overseas leaders are disappearing. In fact, global players such as Heraeus are also building AMB substrate capacity in China. That shows they also recognize the scale of the Chinese market. China's EV industry is too large, and supply chain response speed is too important. If international companies do not manufacture locally, they risk losing share to domestic suppliers. So the new picture is not a simple story of complete domestic victory. It is a transition from overseas dominance to direct competition inside the Chinese market. That transition itself is significant, but there are still real constraints. First, capacity is not the same as certification. A material cannot enter a vehicle just because a sample works. It must pass high temperature and high humidity tests, thermal shock tests, thermal cycling, insulation resistance, mechanical strength tests, and full traceability audits. Entering a vehicle-grade supply chain can take 1 to 3 years. Second, powder remains a critical bottleneck. Some domestic companies can produce silicon nitride powder, but Japanese suppliers still have advantages in ultrafine, high-purity powder, batch stability, and long-term consistency. True localization must include powder, ceramic sheets, brazing materials, equipment, and inspection systems. Third, AMB substrates are still more expensive than traditional DBC substrates. Their strongest application is in silicon carbide modules. Silicon carbide has not yet penetrated every segment of the EV market. Many lower-cost vehicles still use IGBT modules and lower-cost substrate solutions. That means domestic AMB substrates have large potential, but the market will not explode overnight. It will likely grow with the adoption of 800-volt platforms, silicon carbide modules, and higher-end electric drive systems. The core issue is not the short-term capacity of any single company. The bigger question is whether China is filling one of the most important material gaps in the electric vehicle supply chain. China already has global strength in batteries. It has strong momentum in motors and electric control systems. The next stage of competition will be deeper. Silicon carbide devices, power modules, ceramic substrates, and advanced packaging materials. A small ceramic sheet may look insignificant, but it determines whether a power module can become smaller, lighter, more heat-resistant, and more reliable. It affects driving efficiency, fast charging, thermal management, vehicle reliability, and the degree of control China has over high-end electric drive technology. In the past, China's EV advantage was often about manufacturing scale and supply chain integration. Now the competition is moving into materials, devices, and packaging. Whoever controls these foundational materials controls a critical part of the EV value chain. That is why mass production of silicon nitride AMB substrates is not just a materials industry update, it is a signal. Chinese manufacturing is moving from building the vehicle to building the critical materials inside it. And a palm-sized ceramic sheet may be quietly redrawing the security boundary of China's electric vehicle supply chain.